1, 2, 3, 4, 5, 6. All right, everybody, let's get going. It's time to stream. Got to do a whole bunch. This is Physics 1. I think this is 111 today. I think today's 111. The drawer won't go. What the heck? Jeez. I don't think it's supposed to do that. Well, I don't know. Maybe I broke this drawer. 111 new. Let's go. Where's that textbook? I just had it here. Here it is. Oh, gosh. What a day, you know. Okay, so today we're doing forces, and there's a bunch of cool stuff to do, and this stuff is all going to be on the midterm. So I thought we should get it done ASAP. So turn to page 137, and let's start with question 1. Question 1 goes like this. A truck is traveling at a constant 25 meters per second. Oh, here, I should make sure that we're actually streaming. Yes, we're streaming. Okay. So truck, it says, is traveling a constant 25 meters per second when a motorcycle speeds past at a constant 40 meters per second. On which vehicle, if either, is the magnitude of the vector sum of forces exerted on the vehicle greater? So which one is being pushed harder? Both of them have constant velocity, so both of them have constant. So both of them have no change in their acceleration, and so both of them have net force 0. These are supposed to be vectors, but it's 0, so. All right, question 2. You wish to move a crate. Is there a minimum value for the magnitude of the pushing force you have to exert to set the crate in motion? And is there a minimum value for the magnitude of the vector sum of forces that must be exerted on the force to keep it in motion? Okay, so you're pushing on a crate. Here's you pushing with your hands on a crate. Is there a minimum force that you need to get it moving? That's the question. The answer is, are there other forces? There might be a static friction. If there's no friction or no other horizontal force, if your force is the only force pushing it sideways, then F, I guess, let's tighten this up. F push. If the total force is composed of only the pushing force, then the acceleration is just F over m, and you don't need any any force bigger than 0 is going to cause the thing to accelerate. Part B. Is there a minimum value for the magnitude of the vector sum of forces? Vector sum of forces. Now we're talking about F net. Good. Is there a minimum value for the magnitude of the vector sum of forces that must be exerted on the crate to set it in motion? Is there a minimum value for the magnitude of the vector sum of forces that must be exerted on the crate to set it in motion? Yeah, I mean, F net divided by m, it's acceleration. Just like I said up here. Yeah, if there's more than one force, then the thing that will determine what the acceleration is the vector sum of forces. So if there's more than one force and they're all pushing, but they don't all balance out, you will get an acceleration. And so there's no minimum vector sum of forces. Question 7. A worker pushes a box in a factory. In each case, decide which force has greater magnitude. The force exerted by the worker on the box or the force exerted by the box on the worker. Okay, so the box feels a push from the worker, and the worker feels a push from the box. Okay, question 1. The box is heavy and does not move no matter how hard the worker pushes. Well, you know, the force is the rate of change of the momentum. If the box's velocity stays 0, then the worker's velocity is going to stay 0. Neither one has a momentum that changes, so same amount of force. That's a weird way of putting it. I don't like putting it like that. Let me erase it. That's clever, but we're forgetting that the system's interacting with other things, so it's a little bit confusing. There's more than one force on these boxes, because if there weren't more than one force, the box would move when you pushed it. Yeah, anyway, these are the same. Same. Question A is the same. B. Some contents are removed, and now when the box is pushed, it slides across the floor at constant speed. Okay. So A, these two forces, that's what we're talking about. These two forces are the same. And in B, these two forces are the same. And in C, these two forces are the same. Yeah. Now, why is this confusing? This particular question is a little bit confusing because of the way it's posed. We might, for instance, ask you a similar question where we say, which is stronger? The force for friction from the ground on the box, or F push from the guy. Okay? And so in the first case, the maximum static friction is stronger than the person pushing on the box. In the second one, the kinetic friction of the box sliding across the floor is the same as the guy pushing on the box because velocity is constant. And the third one, the worker's pushing harder than the kinetic friction. Okay? So in that case, when we're comparing the force of friction to the pushing force, one can be bigger than the other. But in this question, as it was asked, we're talking about the force that the worker feels from the box and comparing that with the force that the box feels from the worker. And we know that they're the same. No, not 8. What question is it now? 11, I think. A pitcher throws a fastball towards home plate. When the ball is halfway to the plate, is the pitcher's push still exerted on the ball? What forces, if any, are exerted on the ball at the halfway location? Okay, so let's draw this. Here's our pitcher. Standing on a pitcher mound. It's pretty good. Here's the ball. And here is our home plate. All right. So the question here is the pitcher still pushing on the ball? To answer that, we have to think about what kind of force we're talking about. Are we talking about a field force where things don't need to be touching for there to be a force, or is this a contact force? Well, the pitcher throws the ball using a contact force. His hands have to be in touch with the ball. At this moment in time, the pitcher is not touching the ball, so the pitcher is not applying any force. So it turns out that this isn't, in fact, a pitcher. This is a belly itcher. Okay. Part B. What forces, if any, are exerted on the ball at the halfway location? So what are we here? So what's touching the ball? I mean, there's the field force of gravity. What else is touching the ball? If your answer is nothing is touching the ball, then there aren't any other forces. If you're going to say that air is touching the ball, and it kind of is, then there should be a drag force. But we should note here that we're not really going to talk too much about drag force in this particular course. Anyway, so which one's right will depend on context. All right, time for question 19. Oh, I'm gonna check the thing to make sure that nobody has asking any questions. Oh, 2 people are watching. Hello, watchers. Nobody has any questions. Okay, that's fine. Fine with me. So, 19. You are in a stationary elevator, so the contact force exerted by the floor on you is equal in magnitude to the force of gravity exerted on you. Here I am sitting in the elevator. All right. So it says that force from the ground is equal to the force from gravity. When the elevator starts downwards, which forces change? What happens to its magnitude? Well, when the elevator starts, start here is the key word. Well, down is also a key word. But when you start to move in the downward direction, intuition is telling us that you're accelerating in that direction, okay? And that means that your total force has to be in the downward direction. Now, of the 2 forces you feel applying to you, gravity is the same strength as it was before. So it must be that the normal force is changing strength, and in this case, it's getting weaker. Because if that gets weaker, it means that the normal force and the gravity won't cancel out completely, and thus that F net will be pointing downwards, causing a downwards acceleration. Does that make sense? 19. All right, time for question 20. Let's double check here, make sure nobody's got any questies. None. Yes. Okay, so when you are standing motionless on the ground, your feet exert a force on the earth. It's true. Here I am standing on the ground, and there's the earth. My force are exerting, my feet are exerting a force on the earth. Why doesn't the earth move away from me? Well, the answer is that apparently F net for the earth is 0. So there must be another force balancing this out. So the normal force from my feet pushes down, and that means there must be another force pointing up that cancels it out. So what force could pull the earth in the upward direction? Let's think about me for a second. I'm also not accelerating. There's a normal force from the ground, Fn. That needs to match this one. And there's force of gravity. And by virtue of the ground being stiff, this force and this force must be equal and opposite. In other words, I'm looking for a force here, one on the ground, that has the same strength as gravity pulls me. Same strength, but opposite direction. This force is the force of gravity as it feels on the earth towards me. So this is the force of gravity pulls earth towards me. That's a bonkers answer, huh? 29. Question 29 goes like this. In an electric breakdown in air, a spark... Oh, that's what they're talking about. They're like, oh, you got, you know, an electrode here, an electrode here. This guy's positive charge, negative charge. They are talking about a spark. Bzzzt. Oh, wait, that's not what I wanted. Bzzzt. Spark. Okay. So, an electron, which has mass 9.11 E minus 31, experiences an electric force 4.83 times 10 to the minus 3. 13 newtons. The acceleration is going to be the force divided by the mass. 4.83 E minus 13 divided by 9, parentheses, 9.11 E minus 31. Acceleration is 5.3 times 10 to the 17 meters per second squared, which is very fast. Next question. 33. A 50-kilogram pneumatic hammer is filled with a shock absorber, or it's fitted with a shock absorber at the top to lessen the impact on the worker. The vertical displacement of the hammer as a function of time is given by x is equal to 15 times t squared minus 20 times t to the 3. In other words, so here's our jackhammer. That's what jackhammers look like. This part goes up and down. Okay. So what this equation is describing is we're saying, okay, let's set x is equal to 0 here. This equation describes the position of the jackhammer as a function of time. What's the opposite acceleration at 2 seconds and 4 seconds? Wait, no, that's not this question. I'm reading a different question. I'm sorry. Write an expression for the x component of the vector sum of forces exerted on a hammer as a function of time. This is a 50-kilogram hammer. All right. The net force, the total force, is going to be m times the acceleration vector. So I need to figure out what the acceleration vector is. So I take the derivative. Oops. dx by dt, that's 30 times t minus 60 times t squared. And then I take the derivative of that. Acceleration is the d by dt of the velocity, so it's 30 minus 120 times t. Okay, so I'm going to put this and this into this equation. F net as a function of time is 50 times 30 minus 120 times t. Fun. At which values of t is the x component of the vector? That's this guy. Vector sum of forces of the hammer positive, and from which values is it negative? Well, this is a very strange function because you think a jackhammer would be periodic. Let's talk about this graph. It's super weird. I just need you to understand why the answer I'm going to give is so bonkers. So we can factor out 5t squared out of this, and it looks like 3 minus 4t. So at t, at t is equal to 3 over 4, that's when it's going to cross the axis. So this is what it looks like as a function of time. In other words, the top of this jackhammer jumps up, comes down, and then goes to the center of the earth. Okay. So this we want to talk about when this is positive and when it's negative. F net is positive when 30 is bigger than 120 times t. So it's positive for t is smaller than 3 over 12, which is equal to 1 over 4, which is equal to 0.25 seconds. So it's an upward pointing force for 0.25 seconds, and it's a downward pointing force for the rest of the time. And the net force is equal to 0 at time 0.25 seconds. Which is bonkers. Like I said, this is a crazy position versus time graph. But, you know, life's meant to be fun, even if you're a construction worker. Question 39. See if there's a question here. Nobody has any questions. 39. 39 goes like this. The magnitude of the gravitational force exerted on the piano in figure blah is 1,500 newtons. How much force do you have to pull on the rope in order to hold the piano A with the single pulley and the double pulley? Okay, I've accidentally given myself a pulley question, and I don't usually do pulley questions because they are intensely silly, but you know, pulleys are super useful. Okay, so here's the ceiling. I'm recopying the drawing in each of the diagrams. So here you are lifting a piano using a rope like that. And then In this second diagram, you're lifting a piano with a rope that goes around the first pulley, around the second pulley, and then gets attached right there. Okay, and this is 1500 newtons, and there's 1500 newtons. Okay, so the question here, this is actually a question on how formally one deals with tension. And the idea is it's a force exerted by a rope in the direction that the rope is pointing. So in this first diagram, let's talk about all the forces. There's the force of gravity. Oh, come on. There's the force of gravity pointing down, and then a single tension point, Ft, pointing up. The idea being there's only one rope attached to it. Okay. So I'm trying to hold the piano in the air, and that means, well, presumably it starts at 0 velocity. We want the acceleration to be 0. And so if the acceleration is 0, then the net force must be 0. And thus minus 1500, that's the force of gravity, plus the tension force. Tension has to be 1500 newtons. Sometimes, I have no idea why you don't see this anymore. I think these questions are kind of like back in the days when everybody lived on the farm or hauled jeeps in World War II and stuff, when people had to rely a lot more on human strength to do things, you saw pulleys a lot more often. Often in more archaic places, people refer to them as force multipliers. But the idea is that if you hook up a pulley in this particular way, it requires less force to pull on it. And there's a couple of different ways of explaining it, but the easiest way is this. The free body diagram, there's still gravity, but now there isn't just one rope attached to it. Technically, there's 2 ropes attached to it, each pulling with the same tension because it's the same rope. Ft1, Ft2. So F net, I want the velocity to be 0 and the acceleration to be 0, so the net force is going to be 0. And when I add these up, 1500 plus T, that's the tension in the first rope, plus T, that's the tension in the second rope, you end up with the tension being 750 newtons, which is half that amount. And at this point, you might be saying, hey, does this mean that the more we wrap the rope around the more we wrap a rope around a pulley, the less force it takes to lift something? And that is exactly true. So, for instance, here, I'll draw a really complicated pulley system. I'm going to draw it as 3 pulleys. 1, 2, 3. Usually you see them just kind of attached all together instead of a whole bunch of different pulleys all one at a time attaching it, but this kind of helped me explain. All right, so the rope goes up, and the rope comes down, and the rope goes up, and the rope comes down, and the rope goes up, and the rope comes down, and then goes back up and attaches somewhere. Okay? It doesn't have to attach to a pulley. You can attach it to the ceiling. In this case, FG is still there, but there would be, let's count with a pen. 1, maybe let's count with a better pen. 1, 2, 3, 4, 5, 6 tension ropes holding you up. 1, 2, 3, 4, 5, 6. And so F net is equal to 0 is equal to minus 150, 0 plus 6 times t. The amount of force it takes for you to hold the thing up is 1/6 what it actually was. Before I go on, you might want to know what this tool looks like. It's called a bit and tackle. And they look like this. There's just a whole bunch of pulleys assembled inside of a kind of a big weird housing. You know, they look like that. See one of these things in like an old store, backstage, places where people have to haul things around by hand. Yep. Anyway, so that's the deal. And now at this point in the game, you might be like, hey, why do we need to do it with pulleys? Like, if doing it this way with 6 strands increases it with it, why do I need all this pulley business? Wait, no, hold on. I got 2 thoughts in my head at once. So yeah, it works well. Why do you need all these things? Because each individual one, you know, pulls it up. But the question you might ask is, are there any drawbacks to the system? And there are. The person we're talking about, this person is trying to lift the piano, right? So they're lifting the piano up, and that means they're pulling the rope down. In this scenario, if the piano goes up 1 meter, the person has to pull 1 meter of rope past them. In this scenario, for the piano to go up 1 meter, that means that 1 meter of length on both of these has to be lost, and this person has to pull it 2 meters. This person doesn't have to pull as hard, but for the piano to go up 1 meter, you'd have to go you'd have to pull 6 meters of rope down. So there's drawbacks to these things, but it's fun. Anyway. So 39. Wait, no, not a bit and tackle, block and tackle. All right. 46. A bag of concrete is tied to one end of a rope that is looped over a pulley attached to a ceiling. The other end of the rope is tied to a pallet of lumber. The concrete mix has a greater inertia than the lumber. When both loads are released from rest so the system is free to move, compare the tension in the rope with the magnitudes of the gravitational force exerted by Earth on the lumber and the concrete mix. Ignore any friction in the pulley. Woof. That's quite a question. Let's draw this pulley. Here's our ropes. Okay, so the concrete mix has greater inertia than the lumber. Concrete mix bigger than lumber. When both loads are released from rest, so the system is free to move, compare the tension in the rope. With the force on gravity, all right, so how's this gonna go? There might be an elegant way to do this, but I'm not one for elegance. Let's just mush through the mushy mush. you know this one's going to accelerate down, and you know that this one's got to accelerate up. And you know, based on what I just told you about pianos, if this one here goes down 1 meter, this one here is going to go up 1 meter. Okay? So let's set up two force free body diagrams. Okay, lumber. So the lumber has to go up, so the tension M times ML times G. So the lumber has to go up, and that means the tension has to be bigger than the force of gravity on the lumber. Tension, okay, so this one's the concrete. The tension pulls up C times G. Okay, so the concrete's going down, and that means the tension has to be smaller than MC times G. Yeah, I think that's what it wants. It's asking us to compare, and we're saying it's bigger than one and smaller than the other, so good work, everyone. 46, so now 61. 61 goes like this. If you try to pound a nail into a board with a 1.25 kilogram rubber mallet, .5, and you will have less luck than if you use a 0.8 kilogram steel hammer. Why? Oh man, I love this question. Okay, so what this question is really asking us about is force. Which one exerts a bigger force on the nail? On this nail specifically, and not any other mechanism. Okay? So, what goes into force? Well, the force is just the rate of change of the momentum divided by the time, right? Which one has a bigger change in momentum? Well, initially, let's suppose they're both going at the same velocity before they hit, and then after they've hit, let's assume that they have velocity 0. Okay? In both these cases, they don't have the same velocity. I mean, they have the same velocity, but they don't have the same momentum. Rubber, delta P rubber is going to be bigger than delta P steel because it's got more mass. Its change in velocity is the same according to these weird assumptions that we've made, but one has more mass, and so it's got more momentum, and so its momentum is going to change by more. But the force isn't about the change in momentum alone. It's also involves like the rate of change. So delta T shows in there. Which one takes more time? This one or this one? Rubber deforms quite a bit when it's hitting the nail. And so delta T is large. The metal hammer barely deforms at all. Whoa, that's bonkers. The metal hammer barely deforms at all. So delta t is small. And we don't have any numbers to throw into this, but I bet we could make some pretty fun ones if we wanted to. But the long and the short of it is, this fact is going to outweigh the fact that it has more momentum in this case. This question isn't predictive, it's experiential, okay? So it's asking us to not make a prediction. So if I was to ask, hey, based on what you know about masses and changes in velocities, which one would feel the bigger force? I wouldn't know what to say. I'd be like, well, I don't know. I mean, there's a case to be made that this one offers more force, but there's a case to be made that delta t takes more time. And this one has less of a change in momentum, but delta t is much shorter. So there's no way to tell. This question's all about explaining. I know the answer. I know that it takes. I know that you get less. That you get less force in this case out of your big mallet than you do out of your tiny little hammer. And you get less force because even though it's got more momentum, the delta t term is so much larger in the rubber mallet than it is the tiny hammer that that explains why it offers less force, that it's less effective. We know the answer. We're working backwards. We're trying to explain it. Does that make sense? All right. That's a pretty funny question. Last question, 65. A 1500 1,500-pound car goes from 0 to 100 kilometers an hour in 60 seconds. What's the impulse delivered to the car? Well, fun. 100 kilometers per hour. Let's convert this into meters per second. So 1 kilometer, so I need it meters, kilometers. What's the relationship? 1,000 meters is 1 kilometer. So hours into minutes. 1 hour is 60 minutes, and into seconds. Minutes, seconds. 1 minute is 60 seconds. So 100 times 1,000 divided by 60 divided by 60. 27.7 meters per second. Delta P is the mass times delta V. So yeah. 41550 kilogram meters per second. What's the average vector sum of forces? To figure that out, delta P over delta T. So it's going to be 41550 divided by 60. 692.5 newtons. And that clears up the questions I'm going to do today. Actually, you know what? Give me a second here. I think maybe we should do a friction question. I think those are chapter 10. So we might have friction questions on the final exam, just simple ones. But all right, I'm going to add some questions to the list of questions. This is page 184, questions Oh, wait. Question 180. 179. Question 14, 15, 16, 18. '83, 80, 83, 87, 92. All right. So let's do these questions because they're friction questions, and friction questions are fun. So there's some conceptual ones that we should get through ASAP. 14. A common parlor trick is to yank the tablecloth so hard that any dishes and glasses on the cloth stay put instead of falling to the floor. Explains how this happens. Cup, tablecloth, table. Okay, so usually when you accelerate, it's all about accelerations. Usually when you accelerate the tablecloth at a slow velocity, static friction holds the table stuff in place. Holds the objects in place and pulls them forward. If, on the other hand, you pull it really hard, so it's a big acceleration, static friction is too small to hold it in place. F max static friction is too small. That's a smaller than symbol. To keep the stuff in place on the tablecloth. And thus the tablecloth slides under the object independently of it. And the objects don't actually stay in place. They will move just a little bit. But when they move, they're not accelerating for very long. The kinetic friction isn't that big, so it slides it forward, but not for very long. Okay, question B. Why, if you pull on the cloth too slowly, do the dishes and glasses get dragged off the table? Because if you go slow, static friction's enough to hold it in place on the tablecloth. Question 15. When a car accelerates gradually, no squealing tires, is the friction between the tires and road kinetic or static? It's static. So the deal is, it becomes a lot more obvious. There's something called rolling motion. I'm not sure if we have enough time to talk about it this year because it's a little bit subtle. But what you do is, if you take a wheel and it rolls without sliding, What? Apple Pen. What's wrong with you, Apple Pen? %. No, you should be working. Maybe it needs to reconnect. Hold on. can work in this program. Okay, great. So that program is janking up. All right, well, is this even the notes program? Where's the notes program? All right, so there's an effect called rolling without slipping, which is a type of motion that, you know, car tires do. So let's imagine we got a car. Here we go. The wheel's moving forward with velocity. Okay. But it's also rolling as it does it. Okay. And, oh, shoot, I forgot to plug this back in. Hold on. No. All right. There we go. So yeah, you have a tire and it's rolling. It's not only moving forward, it's also spinning. But then the neat thing is, if you keep track of where a particular point on the tire is as it rolls, what you see is that it doesn't, the part of the tire that's touching the ground doesn't really move while it's in contact with the ground. Instead, it the relative velocity of the tire, sorry, how should I say it? The tire as a system is moving forward, and the tire as a system is moving forward, but the points on the tire are moving, because the tire's spinning, the points on the tire are moving relative to the tire. Right? And then it turns out, if you work through the math, that this velocity and this velocity are the same. And so this is a relative velocity, and it means that the part of the tire touching the ground doesn't actually move while it's in contact with the ground. And that's how rolling works. Like, literally, that's the basics of lots of wonderful things come of it. From this, you can get a relationship between how fast the tire is spinning versus lateral motion. Yep. So it's an important aspect, but there you go. That's the answer to your question. Now, what's the next one? The next one is question 16. Figure 4.16 represents two stroboscopic pictures. So here's one picture. Block, 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 block. And B looks like block, 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 block. Dang, how am I supposed to draw these apart? Okay. In one sketch, the block is released from rest at the top of the ramp and moves downwards. In the other sketch, the block is placed at the bottom of the ramp and shoved up the ramp. Which sketch is for the downward motion? Which one for the upward motion? So obviously this is the friction section. The question here is, which one has a bigger, so what we're going to do is we're going to try to figure out what their accelerations are. Both of them are accelerating downwards. But this downwards acceleration comes from a combination of forces. Oops. So in one of them, there's gravity. Normal force is there. And then friction's pointing that way. In the other one, the normal force is still there. Gravity's still there. Friction's pointing in the other direction. Okay? So in one of them, they're going to have an extra big acceleration downwards, and the other, they're going to have a smaller acceleration downwards. Which one is which? Presumably delta t is the same in both cases. So, you know, in part B, it travels farther in that delta t. This one, it travels farther. You know, the distance between any two, that one's bigger than the distance between these two. So that lets me guess that the acceleration in this one is bigger. And so in this one, it corresponds to this case, and so this one is moving uphill, and this one is moving downhill. But you can't tell that from my crappy drawing because it's not a good drawing. 16, 18. In figure 10.18, all surfaces experience friction. B, A, C. Is the magnitude of the horizontal component of the force exerted on A... Oh, okay. Is the magnitude of the horizontal component of the force exerted by A on B greater than, equal to, or less than the magnitude of the horizontal force exerted on A by A on C if the system of blocks is moving at constant velocity to the right and B accelerating to the right due to an external force exerted on B? Okay, so let's try to get things straight here. We want to know about the force on B from A, and we want to know the force on C from A. Okay, so we want to compare them. Part A, moving with constant velocity to the right. If they're moving with constant velocity to the right, F net is 0. There's nothing pushing on them. And so FC is going to equal FA is equal to 0. Fine. B. Alright, so in question B, we imagine that there's a person over here pushing on block B. Or it's a living. Okay, so which force is bigger? Okay, so how do I break down the answer in terms of concepts that we've covered in the class? Let's talk about the forces on A and C. Okay, there's the normal force. So the whole system is accelerating to the right. Okay, granted? Okay, good. So there's the normal force from A onto C. There's gravity. There is the force from C that we want to talk about. Okay. Now, what are the forces on A? There's the force of gravity. There's the normal force from B. There is the push from B. FA from B. I'll call it FB. That's the push from the friction on B. Okay? That's not all the forces on this object. There are also pairs of forces which come from interacting with C, right? So A pushes C upwards, so it's going to have a pair to this particular force. Call it F and C. And this is a force from A onto C, so it's going to have a pair. Does that make sense? Why is this important? It's important because both block A and block C have the same acceleration in that direction. And I don't know what their masses are, so I can't tell what F net is on either of them. But I do know that the total force needs to have an x component in that case, and the total force needs to have an x component in that case. And that means that this force has to be stronger than this force, okay? So that the net force on this guy pushes forward. So let me write that down. Thus, FB has to be bigger than FC. Why is this relevant? It's because this force has a pair, just like these ones did. The pair to this force here, though, is that one. The force from force on B from A. Okay? And that means that the force from B from A has to be bigger than the force on C. Isn't that fun? Yes, it is. Please learn how to reason that way. This is a great question to put on a test if I want people to not get it right. And the question you have to ask is, do I want people to get the answers on the test right? You would be surprised. Okay, you walk down your icy driveway without sliding. If the incline of your driveway is 15 degrees from the horizontal, what must be the coefficient of static friction between the shoes and the ice? Okay, so I don't slide, and that means my net force is 0. Fg, and then there's Fn, and then there's F static. All right, well, I am going to decompose the system in terms of I hat and J hat. I hat, J hat. So when you do that, the force of gravity is mg, let's see, that's 15. It's going to be mg cosine 15 times minus j hat plus mg sine 15 I hat direction. If all the forces balance, then F static friction is going to be minus, alright, I'll call it F in the minus I hat direction, and the normal force is, I'll call it N in the J hat direction. if my acceleration is 0, then it means the net force is going to be 0 I hat plus 0 j hat. And now I combine them term by term. So 0 is equal to, here's the I hat terms. 0 is equal to mg sine 15 minus f, and the j hat term is mg cosine 15 minus plus n. So the strength of the normal force has to be mg cosine 15, and the strength of the friction force has to be mg sine 15. Okay, so there's no maximum for the static friction coefficient, but we do have a minimum. And the minimum static friction would be if this number were the maximum static coefficient, which would be mu static times n. In other words, mu static times mg sine theta. Oops, that's not right. Mg cosine 15 is equal to mg sine 15, and you can rearrange that to tan 15, which you can calculate. So this value isn't what it must be. This number is the minimum static friction coefficient. Okay? If it's any smaller than this, I'm going to slide. That's the idea. So that is question 80. Time to do question 83. A resort uses a rope to pull a 55-kilogram skier up a 40-degree slope at a constant speed for 100 meters. Calculate the tension of the rope if the coefficient of static friction between the snow and skis is 0.2. How much work? Don't worry about the work. Let's just do part A. That's question 83, right? A. All right. Time for a free body diagram. There's tension. Oh, someone's knocking at my door. Hold on, please. Oh, here, what's up?
Oh, are you tasty?
Yes, I am. What can I do for you?
I was just wondering if I could scan, but if you're busy.
Oh, you can. Here, I'll give you the things. This one, and this one, and this one. Here you go.
Sorry.
Okay, see you. Tension, right. And you're going uphill, so friction points that way. And the normal force goes that way. And gravity goes this way. And this angle here is 40 degrees. Okay. I'm going to show you a procedure. It's a procedure I use with my 112 class, and it's really good. Because sometimes people have trouble starting these questions. And there's kind of an order that if you write everything out in this order, you can see what you have on hand and what you're missing. So, you start with the acceleration. What do we know about this motion? So the first thing to deal with is the motion. Are we accelerating? Do we know what the acceleration is? You write down what you know about the motion. This is constant velocity. If something has constant velocity, it's got to have zero acceleration. 2. Once you have a sense of what the acceleration is, sometimes you know it, sometimes you don't. Sometimes you know what direction it's in, and you have to assign a variable. Now we're going to talk about the total force, F net. This part of it, all I'm going to do is I'm going to multiply the acceleration vector by this. I want to know what I do and don't know about the net force. And in this case, it's a 55 kilogram skier. So it's 55 times 0 is 0, and 55 times 0 is 0. Step 3. Step 3, I list all the forces I know. I essentially draw a free body diagram. I've kind of already done step 3, but then the next part is you write out the components of the vectors. And to be honest, part of step 1 should have been me deciding what the axis is. So I'll call this direction the I hat direction, and I'll call this direction the j hat direction. Okay. So that means that ft is only in the I hat direction. I don't know how big it is, so I'm going to assign it a variable, t. Fn is only in the j hat direction. I don't know how big it is, so I'm going to assign it a variable. F friction, I know which direction it is. It's in the minus I hat direction. And if I knew what n was, I would know what it is. So I'm going to fill that in. The coefficient of friction is 0.2 times n in the minus I hat direction. And then gravity, in these tilted coordinates, it's going to be 55 times 9.81 times cosine of 40. That gives me the minus y hat direction, so it's minus 413 in the j hat direction, and 55 times 9.81 times sine 40. This is minus 347 in the I hat direction. Okay. Step 4 is I put them all together. I put all these terms together and I put them together with this. So F net is 0 I hat plus 0 j hat, and that's equal to t I hat plus n j hat minus 0.2 n I hat minus 413 j hat minus 347 I hat. And I mean, this has a lot of moving parts to it, so I'm going to write each vector term separately. So the I terms are 0 is equal to, and now I'm going to gather every term that has an I in it, and I'm going to write them all down. So this is t, t minus 0.2 times n, whatever that is, minus 347. J, that's n minus 413. So now I just solve these equations. The normal force has to be 413, and that makes this whole equation 347 15 times 0.2 plus 83 is equal to t. So t is equal to 347 plus 83. 430 newtons. That's what the normal force has got to be. So yeah, you can use this procedure on any force question. You see me doing it a lot in class. 87. The coefficient of friction between tires and dry pavement is about 0.8. Assume that while traveling at 27 meters per second you lock your brakes, and as a result, the only horizontal force is a frictional one. How many seconds does it take to bring your car to a stop? So here's your car. It's traveling with this velocity to the right at 27 meters per second. Whoa. Hey, have you noticed they didn't tell us how much mass the thing has? Weird. Well, let's go. Alright, so what do we know about the... Alright, I hat and j hat. Start with those. I'll make I hat go in that direction and j hat go in that direction. I'm going to use the same practical problem-solving technique as I did here, just to sort things out. 1. What do I know about the motion? It's accelerating. Because you stop the brakes, you want to slow down. So the acceleration in the x direction is got to be I don't want to leave the ground, so the acceleration in the y direction is 0. And in the x direction, I don't know what it is, so I'll call it minus a. So the acceleration vector is going to be minus a I hat plus 0 j hat. 2. Net force. You know some stuff about the net force if you know stuff about the acceleration. Now's the time to focus on that. What does the acceleration tell you about the net force? It tells us that it's going to be a times the car's mass, whatever that is, plus 0 j hat. 3. What are the different forces on it? Let's label them all. There's gravity. There's the normal force. And there is the friction force. What do I know about these? Gravity, that's minus 9.81 times my mass, whatever that is, in the j hat direction. So it goes down. Normal force, I don't know how big it is, but it's going in the upwards direction. And the friction force, I don't know what that is, but if I knew what this was, I could figure out what the normal force is. So I'm going to write that as 0.8 times the normal force, n, in the minus I hat direction. Okay. Now I'm going to put all of these together with this. That's step 4. So let's jump to the case where I just do the I hats and the j hats separately. So it's going to be minus a times m, whatever those are, 0.8 times n minus 1. And then the other one is 0 is equal to minus 9.81 times n. Alright, so that one tells us that the normal force is 9.81 times the mass. And then I can plug this into that term. Acceleration times mass is equal to 0.8 times 9.81 times mass. Oh, hey, look, the masses cancel out. What a coincidence. You know what this means? It means it would take longer to stop if I was on Mars, where the gravity is weaker. 7.85 meters per second squared. So from this, I can tell my acceleration is going to be minus 7.85 meters per second squared. What's the question? Question is, how many seconds does it take to bring my car to a stop? Oh, hey, kinematics. V is equal to V naught plus AT. So the initial velocity is 27 minus 7.85 times time. Set that equal to 0. T is equal to 3.4 seconds. Weird. Alright. Part B of this question says, hey, if instead the coefficient of friction was 0.25, how long would this take? Well, I can cut to the chase. The calculation is going to be exactly the same, so the acceleration has to be 0.25 times 9.81. So that's 2.45. So the acceleration vector is going to be, I call that I hat, minus 2.45 meter per second squared I hat. So the velocity is going to be 27 minus 2.45 times t. Set that equals 0. 11 seconds. How far do you travel in this time interval? I guess you can just figure that out, right? Delta x is equal to v naught t plus 1/2 a t squared. So that's 27 times 11 minus 1/2 times 2.45 times 11 squared. $149 meters. That's pretty far. 87. All right. So now it's just question 92. 92 goes like this. You're pushed down on a book of inertia m resting on a table with a force directed at angle theta away from the vertical. The coefficient of static friction between the book and the table is mu s. If theta is not larger than some critical value, you can't get the book to slide no matter how hard you push. What's that critical value? All right, so what are they talking about? They're saying, imagine you got a book, M, and you're pushing in that direction, okay? There's going to be some friction force opposing the push, okay? And the deal here is that the strength of this friction force, I mean, there's a maximum friction force, which is equal to mu static friction times the normal force. And if you're pushing down on it, the harder you push down, the larger n is going to be. And so the larger F max is going to be. And it's going to be more and more difficult to overcome. Okay. So let's look at the case where the friction force is equal to the maximum friction force. We'll do the analysis technique I showed you. In this case, it's borderline not moving, so the acceleration is going to be 0. If the acceleration is 0, the net force is going to be 0. What are the forces on this thing? There's a static friction force. There's a normal force. There's a gravity force. And there's a pushing force. And the angle we're looking for is theta here. Okay. So, let's F static Fn is, all right, right. That's what I was trying to remember. Let's define some terms here. I hat in that direction, J hat in that direction. Good. No, J hat up. I hat sideways. All right. So the normal force is going to be N in the J hat direction. I don't know how big N is. The static friction is going to be mu N minus mu N J hat direction. Fg is, of course, mg. And F push minus J hat. And F push is going to be, I'll call it big F, which is the amount I'm pushing, times sine of theta in the I hat direction minus f times cosine of theta the j hat direction. Okay, and now we put it all together. So the I hat terms, they look like they all add up to 0 according to this. So that's, oh, come on, I had one job. So that's minus mu n f sine theta. And j, they add up to 0, and it's little n minus mg minus f cosine theta. So you solve this for little n, mg plus f cosine theta, and then this equation becomes equals okay, so okay, so the claim of this question is that for some value of theta, there isn't a force big enough to solve this equation. So let's solve the equation for f. Sure, why not, eh? Mu mg plus mu f cosine theta is equal to f sine theta. So now we rearrange it. Mu mg is equal to mu cosine theta plus sine theta times f. In other words, one way to think about this is f, the solution f, tells me how hard I need to push at some angle. How hard to push. Mu mg over mu cosine theta plus sine theta. All right, so let's think about what what the behavior of this function does. Wait, pardon me. There's a slight mistake in this, and that's that this is supposed to have a minus sign in it. Okay, there we go. So the deal here is that if I were to graph the force in terms of theta, there's going to be an asymptote here where the where denominator is 0. Okay? And if the force is any, or if the angle is any bigger than that, then the force, then the force would be negative, right? Because I know that there's going to be some, there has to be cosine theta is equal to sine theta. There has to be a solution to this. So the denominator here is 0 somewhere. And then so on one side of it, the force here is negative, the other is positive. What does negative force in this case correspond to? It corresponds to pulling the thing upwards instead of pushing it, reversing the direction of that force. In this case, we specified that you have to push, and so what that means is, in this part of the graph, I'm sorry. in this part of the graph, there's no value of f, positive f, that's strong enough to move the object on the table. What's that value? Mu is equal to sine theta over cos theta. That's where the denominator is 0. I guess we call it a critical value. So that's tan of theta c. So theta c is the arctan of mu. All right, well, that was it for the questions for this week. And hopefully they should put you in good stead in preparing for the midterm. Have a nice week. I'll see you in class.